Okay, so what I'm going to show you in this video is a PhET simulation. It's going to try and demonstrate what goes on with some of those rays as they pass from a light source, which we'll call an object, through a lens, and then they pass to meet behind the lens. And so what I have here is I've clicked a few things. I've got mini rays, and you can see I can adjust the radius of curvature of this lens. So a lens that is fatter will bend the rays more impressively than a skinny lens, and so that will change how they behave in the wake. I could also change the refractive index of this lens, so changing whether it is something that really slows down light a lot with these bigger refractive indexes or not very much. And I can also make my lens larger in diameter, so I can make it larger and smaller. Okay, so I'm going to kind of put things all in the middle of the road. And right now I have many rays, and they're all converging in a spot. And here would be the location of a screen. And if I had my screen right here, I would see a fuzzy image, okay? But if I put my screen right here at this special spot where these rays converge, this would be the location of an in-focus image. And while I have this up here, I'll remind you that this might be what goes on with some of your eyes that need glasses, okay? So this distance here between the lens that is in your eye and the screen, your retina that is in the back of your eye, is a fixed distance. So if your eye is not great about focusing things, maybe it makes the location, maybe your retina is here. And so if your retina is here, you might just need a corrective lens to put in between the outside world and your eye in order to change the light so that it can focus where it needs to be focused. So when we draw ray diagrams, we don't draw all of the rays. We pick out 3 principal rays, okay? So I'm going to click here to turn on, instead of mini rays, I'm going to just draw principal rays. And there's my 3 principal rays. And you can see that actually these 3 principal rays, they don't even all go through the lens as I have drawn them. I'm going to make my lens a little bigger so it doesn't seem so weird. So we have 3 rays. The first ray goes in parallel and out through F. So these little yellow X's must be the focal point of the lens. The second ray goes in through F and out parallel. And the third ray travels in a straight line like this. And it doesn't bend as it passes through. And if you've drawn all 3 of your rays correctly, then they will meet behind the lens and they'll cross in a single spot. Instead of having a screen here, I'm going to do this. So it looks more like what our ray diagrams look like. So we draw ray diagrams as in arrows. So we have a pencil here instead of an arrow. But we draw rays coming out of the tip of the object, traveling through the lens, and then finding their way in the back. And this is a pretty cool thing to play around with. I definitely encourage that you check this out. This PhET simulation just runs with Flash Player on a browser window, so you don't have to download anything to make it work like you do some of the other ones. And so you can see that right as this gets closer, my image is always upside down, right? But as I get closer and closer and closer to the focal point, I get closer and closer. I get a larger and larger image until eventually my image has just gone off the screen. But what happens at a spot right here is kind of special, which is that now if you look here, if I put the object right on top of the focal point, these rays that are exiting the lens are exiting parallel to the lens. That means that they will never cross, right? No matter how far they go, they will never cross. If I get any closer to the lens, now not only will they never cross, but they're spreading out as they exit the lens. So closer to the lens, they're diverging behind the lens. Over here, right, they're converging as they exit the lens. And we've previously talked about the ability to have a virtual image. And this is exactly what we have here, is that we have generated a virtual image. So now if I check this virtual image box, you will see that we can take our 3 principal rays and trace them back following straight lines behind the lens. And it seems as though there is an upright and very large image coming from this direction. So my image gets bigger and bigger and bigger and bigger and bigger until eventually it gets so big that it doesn't exist anymore. And then after that, we have a real image that is formed. And that real image is always upside down. It can be small, it can be big, right? It can be big or small, but it's always upside down. Okay, so let's do a couple of examples here. So try to answer this question. And I'm going to do this as a demo. So I've got this set up as I had in the beginning. So I have my light bulb is shining light through this lens, and it's making a pretty in focus image of the light bulb on the wall. And if I remove the lens, well, you all know what that should look like, right? A light bulb with no lens. There's now no more image on the wall. So that has happened. The next question that we're going to ask is the question of what happens if I put a piece of paper between the light and the lens, but I don't cover up all of the lens, I just cover up the top half of the lens. So take a minute and come up with your guess, and then I'll show you that. So if you've got your guess, if you don't have your guess, pause it. If you do have, once you have your guess, I'm going to go ahead and start this here. And I want you to watch what goes on with the image on the side of the... I've covered up half of it now. And you see the image is still there, but it's dim. And now I've covered up all but just a teeny tiny little bit of it. And you can see that actually the image is still there, but it's really dim. Okay, so we don't need this whole lens to make an image on the wall. We just need a teeny little part of it, okay? So if the light passes through any portion of the lens, the whole image will be there. The bigger the lens, the brighter the image. And we happen to have some lenses just like this inside our eyeballs. Right? We have convex lenses that take diverging packets of rays of light, and converge them to make images on the back of to make real images on our retina. And what do you do when you go outside and it's too bright? You squint your eyes. And if you actually try it right now, you can kind of close your eyes, close your eyes, close your eyes. Your eyes have to be slits before it impacts your field of view. You can still see everything with your eyes half closed. It's just dimmer. So the same thing goes on. All right, so here we said that there was no image at all when we removed the lens. And here we said that if we took our piece of paper and covered up half of the lens, what happened was that we would have a dimmer but otherwise unchanged image. We don't see only the top half of the image or only the bottom half of the image. We see the entire image, but it's just dimmer than it was before. So this is what happens in our eyes. So you have inside your eyes these ciliary muscles that pull on the lens, and they can change the shape of your lens. So if you need to have a very thin lens, You pull tightly on these. If you want to have a very fat lens, then they don't pull as hard. So as light comes in order to make light always form a real image here at the back of your eyeball, right? There's a set distance between here. Those ciliary muscles will kind of cause the lens inside your eye to get fatter or skinnier in order to make the image converge on your retina. And yeah, okay. Some of you need corrective lenses, and most of you are farsighted. That's the typical way that we tend to be. And so what we need to do is what our eyes are doing is this, is that our eyes look like this and they are making an image, not back here on the retina. What is here on the retina is a fuzzy image that is not in focus because the in focus image is all the way up here. So you need to have your lenses are too fat. They are not skinny enough. Welcome to the world, eyes. Everybody's too fat. So we put a diverging lens in front of your eye, and that spreads the light out a little bit and makes it so that your too fat eyeball can focus things down there. And actually, if you remember what kind of images are formed, if it's a real image, and it has to be a real image right here, right? We need rays to be really crossing right here. We can't have a virtual image, imaginary things crossing right here, or we won't be able to see it. Your eye can only see real images. So it takes these packets of light and it focuses them to make real images. I have it written right here, is that this image is always going to be upside down. So you may not know it, but what your eyeball sees is upside down. So here is, geez, that's a real image of me as I get farther and farther away. Let's see if we can find an upside down image. There we go. There's an upside down image of my hand. So this is the image that is being formed on the back of your eyeball. It's upside down. And your brain is smart enough to know how to just flip it. And they've done some crazy experiments with people where they'll like give them a set of glasses to wear that flips everything upside down. And it only takes a matter of hours before your brain figures out that that's upside down and it flips it back. So you can put on these glasses that are upside down and your brain just figures it out. And pretty soon upside down looks right side up and you don't even know any different. Brains are pretty cool things. Okay, so drawing ray diagrams for images looks like, for a virtual image looks like this. And I think rather than trying to draw a ray diagram for a virtual image from this video, we will do it as a problem. So let's do it. We're going to use a magnifying glass. Here's a magnifying glass right here to see a flower better. And it looks like that. So I hold a 6 centimeter focal length magnifying glass 4 centimeters from the flower, and we want to figure out what is the magnification. All right, so the same formulas that we used for mirrors are the formulas that we use for a lens. And I'm only really doing a couple of examples in these lecture PowerPoints. There's more examples in the recitation videos as well. So I've got all the different kinds of ray diagrams that you would want to do in the recitation videos. This is just to give you a taste. So I'm going to use this same formula here, and we're going to learn from our lesson that we did with the mirror. And let's use the formula first to figure out how we should lay out what's going on here. Okay, so I have a 6 centimeter focal length magnifying glass. So that is F. It's 4 centimeters from the flower. Okay, so that is the object distance. And we want to figure out what is the magnification. And rather than just finding the magnification, let's just find everything. Okay, so we'll find the magnification and we'll also find the object distance. Okay, so let's solve for DO. So I'll subtract DI from both sides, and let's work over in a region where I won't have to have anything. So we'll say that 1 over DO is 1 over F minus 1 over DI. And then I take the negative 1 of both sides, and I can say that DO is that. Okay, so let's plug in some numbers. So it's 1 over F, so 1 over 6 minus 1 over 4 to the negative 1. So I'll go 6 to the negative 1 minus 4 to the negative 1, and I'm going to push enter there, and then I hit that to the negative 1 power, and I got negative 12 centimeters. What is going on with this negative here? We did nothing wrong with our things here, but how do we have a negative image distance? And I just realized something that you might have already realized, which is that I solved for the object distance, but I already had the object distance. I didn't have the image distance. So rather than solving for DO, I want to be solving for DI. And fortunately, that doesn't change much. So if I'm solving for this, then DO will be on the right-hand side, and DI will be on the left-hand side, and it just looks like that. Okay, so this tells me that this will be a virtual image. Has a negative image distance. Okay, so that means on my regular old, the problem with all these pieces of paper is that they get lost. Okay, so this is what we would draw for sort of a normal case, where the object is this way, and here's going to be a real image that really crosses. So a real image is that the rays pass through the lens and then they converge behind the lens to make a real image. So a real image will be over here on the right. A virtual image will be over here on the left. Okay, so I know that I need to be able to resolve something that is 12 centimeters, and that 12 centimeters needs to be on the same side of the lens as the object. Okay, so I need to be able to resolve 12 centimeters to the left of this. So that's what I'm going to do. And actually, it seems like maybe my scale just being 1 to 1 works pretty well here, because it's not easy to see from my, my clear ruler. Actually, this number right here is 12. So I can just barely fit all 12 centimeters on my piece of paper. So I'm going to do that. Okay, so here is 0 centimeters away from the lens. There's 1, 2 centimeters, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, so there is my, those are all the things that I expect to need to be able to draw. I'll go ahead and put those same 12 centimeters on the other side of the lens, just so that I'm labeling everything. So there's 1, 2, 3, 4. Okay, so let's draw everything, and I guess we can figure out the magnification. So let's do the magnification. So magnification formula is negative DI over DO. And that will be negative. My image distance is negative 12. And my object distance is 4. So the two negatives cancel, and I will get 3. Okay, so my image is going to be 3 times bigger than my object. All right, so let's see if we can make that work from a ray diagram. So the focal point is 6 centimeters. And unlike for a mirror, I need to draw focal points on both sides because there are focal points on both sides, right? The rays are going to actually pass through this lens. So we need to be able to resolve the left-hand side and the right-hand side. So that's where the focal point is. And we will say that my flower is 4 centimeters away from the lens. And I am expecting that the image is going to be 3 times bigger than 4 centimeters. So it's going to be right here, 4 centimeters away. Right, so this is DO, the object distance. And I'm going to draw it not too tall because I know that I'm expecting there to be an image over here that's going to be 3 times as big as this arrow. Okay, so I'm already maybe pushing the limits of how tall I should draw this arrow. So a little bit of math has really helped me considerably in how I'm going to set this up. Okay, so let's follow the rules for how we draw a ray diagram. And they're going to be a little bit different than what is here, but we'll figure that out. So in the recitation video, I have a ray diagram that I did for a sort of typical case like this. So that might be a better one to start off with than this, but you have to do them all eventually anyway, so you may as well look at it this way. So the first ray goes in parallel and out through F. So let's do that one. So I'll have my first ray goes in parallel. And you know what? I'm actually going to start with the third one because the third one is the easiest one to get right. This one that travels out of the object through the center of the lens and continues on in a straight line. Let's do that one first. So I want it to pass out of the object and then through the center of the lens right at the axis of the lens. Let's do that. That goes like that. Okay, now let's do the one that is in parallel and out through F. I'll go in parallel, so it leaves the object, it travels in toward the lens, going parallel to the axis of the lens, and then it bends, and the light goes out through F. And let's look and see where we are, which is that both of these rays that I drew have light that that's exiting the lens, but they're never going to cross. These two rays are spreading out as they exit the lens. So in order to find the location of the lens, of the image, we need to trace back these two rays that are exiting to see where, over up here, it seems like they were coming from. So let's do that. Take them all the way back like that. And now let's take this one all the way back like that. And there we go. And there are 2 rays, but 2 rays will always cross. So we want to make sure we can get 3 on here. But if you follow this back, we've done a pretty good job because we expected at 12 centimeters for there to be an arrow, an image that was 3 times bigger than my object. And it's looking pretty good. So let's get the third ray on there, which is this one here. It's going to pass from the object in through F and then out parallel. And this is the one that's going to be tricky for us to draw because it's not going to look just like this one. Okay? And the reason that it's not going to look just like this one is because we can't go out of the object in through F and then out parallel. It doesn't work. Okay? So we need to think differently. It's going to still be an in through F and out parallel ray, but the F is this one back here. So let's do this. Right? So it's still going to go in through F, but since the F is back here, we'll sort of imagine a ray that instead of starting at the object, it starts back here at the focal point. It travels up through my object, and then it travels this way. And then it bends and goes out parallel. And I already know to expect this is going to be a virtual image. So I'm going to go ahead and trace this back to see what it would look like. The virtual image location. And there we go. I have my 3 rays, all are converging right here. So the location of my virtual image looks like that. Right, the magnification is 3 times as big, and I have 3 principal rays on here, and it's near enough to 12 centimeters to count. And this negative here has told me that I know it was going to be a virtual image, so I expected it not to be on the normal side, but to be on the abnormal side, just like that. Okay. So let's go ahead and get rid of those. These are just the slides that are on the PowerPoint that go through the same solutions we just went through. We can also have a diverging lens. So a diverging lens is a lens that instead of making incoming parallel rays come together behind the lens, it spreads them out behind the lens. So this is a diverging lens is always a concave lens, one that curves in the middle. And if you are farsighted, then the lenses that you use in your glasses or your contact lenses are diverging lenses. We still have this rule that rays that come in parallel bend and go out through the focal point. But for this diverging lens, we're going to imagine them bending out as though you could trace them back to a focal point back here. So it's a little bit different than it was before. And I think this would probably be a great time for me to get the ray box out and show you just a little bit more about how the light is bending as it passes through different kinds of lenses. There we go. So I have a couple of different kinds of lenses. I have some incoming rays that are parallel. So here is my diverging lens, and here is what my converging lens looks like. Okay, so my converging lens takes rays that come in parallel and it bends them so that they all cross together at this point. So I could measure this, and that would actually be the focal length of this lens. It's, I don't know, 16 centimeters or so. Here is the diverging lens. And if you see, actually, it's spreading these rays out. And if I put these two right next to each other, move this just a smidge. Right, the rays are coming out of the diverging lens spread out, but actually these two lenses are opposites of each other. So just as much as this is spreading out the rays of light, this is focusing the rays of light. So the rays of light that exit both lenses together are actually just parallel as they would have been in the first place. Okay, so diverging lens looks like this. It spreads out the light. And converging lens looks like this, and it puts together the light. In a regular year, we spend 2 weeks in lab just doing labs, optics with this stuff. And so we're going to do our best to get some lab-like experiences, but it's not going to be quite as good as this. So, I really encourage you to spend time with that PhET tool and, do your best to kind of get your hands on things as much as you can, even though a lot of this stuff you can't do as well as you would have been able to do in lab. Okay, so let's get this back up. And so I have to draw a principal ray diagram for a diverging lens like this. We're going to have those same three rules that we have always, but once again, the way that we implement those same three rules is going to be a little bit different. So again, we have that one ray, which is our happy ray, that is easy to draw, that goes straight through the center of the lens and it passes out without bending. So for a lens, I always draw this ray first because it really helps orient me. Okay, and then we have our rays, one that is in through F and out parallel, and one that is in parallel and out through F. So this will be our in parallel and out through F. Okay, this doesn't look like it goes out through F. The way that it is going out through F is that it is going out through F like that. So it is bending, and it looks as though it came from this F on this side of the lens. So that's our in parallel and out through F. In through F and out parallel is this one. So in through F looks like that, but I don't have a ray drawn there. For a diverging lens, we are looking over here at this F. So we'll go in, not quite through F, but in toward F, and then when it hits the lens, it bends and it goes out parallel. And then we'll take all three of these exiting rays and trace them back to see where they came from, and that will be the location of a virtual image. And a single diverging lens will always make a virtual image. So let's do one. Let's demagnify a flower. So I have a diverging lens with a focal length of 50 centimeters, and we're going to place it 100 centimeters from the flower and figure out where is the image. So let's do some math first. So we'll use our 1 over DO plus 1 over DI equals 1 over F formula just to figure out where we expect to see images. So the focal length is 50 and the object is 100. So let's solve for DI. If I solve for DI, I will get that DI is 1 over F minus 1 over DO, that whole thing to the -1 power. So I'll plug in numbers, and I'll have 1 over 50 minus 1 over 100 to the -1. And I get 100. And I have done something wrong, which is a tricky thing about diverging lenses, which is that for a diverging lens, to use this same formula, we're going to put it in as a negative number. Okay, and that's just a convention that we need to remember. So what we're trying to do is for diverging and converging lenses, for convex and concave mirrors, we want to be able to use the same equation. So we don't have to remember different versions of the equation. But because of that, we need to kind of make up some sign conventions. Okay, so if it is a diverging lens, instead of putting in 1 over 50, well, I shouldn't put a negative there, but what I should do is put a negative here. Okay, so let's try that again. So I will say -50 to the -1 minus 100 to the -1, and then that whole thing to the negative power. So this is not 100 centimeters, but -33 centimeters. Okay, and so if one thing that might be a gut check on this is that I know a virtual image is always going to be formed from a diverging lens like this. So I should always be getting a negative image distance because the negative tells me that this is a virtual image. Okay, So the negative tells me this is a virtual image, and now I have a negative. So when I got out a positive, I immediately said, okay, what did I do wrong? I must have missed something. And that's where I backed it out. Okay, so I am expecting that the focal length is 50 centimeters. I need to be able to resolve 100 centimeters, 50 centimeters, and 33 centimeters. So 100 centimeters is the farthest thing that I need to be able to do. And everything is going to be over here, right? The image and the object are both going to be over here. So I need to be able to get 100 centimeters away. So I want to be able to put 10 marks on my piece of paper. And once again, this scale is a pretty easy scale to think of. I've got my centimeter scale here, and from here to here is 10 centimeters. So I'm just going to go ahead and say that my scale is that 1 centimeter equals 10 centimeters. Right, so 1 centimeter on my ruler will be 10 centimeters on my in real life, and that will allow me to go 0, 10, 20 centimeters, 30, 40, 50, 60, 70, 80, 90, 100. I'll go ahead and put them on the other side too. Like that. Okay, so now I have a scale drawing of what's going on here. And now I'm ready to just put things here. Something that people do when they're first learning how to do this is they don't make all these spaces equal. Don't do that. Every single one of these spaces needs to be equally spaced. Another thing is that they'll start measuring from here. You don't want to start measuring from where you drew the location of the lens. That's a subjective spot. You start measuring from this line right here that goes straight through the center of the lens. Okay, so that is where 0 is. Okay, and we're going 10 centimeters away in either direction, like that. Okay, so I have a 50 centimeter focal length. So I'm going to go ahead and put an F here and an F here. And the flower is 100 centimeters away. And let's go ahead and calculate the magnification so that we know how big to draw this arrow. Right? I don't want to draw a teeny tiny arrow if my image is going to be smaller than my object. But I don't want to draw a giant arrow if I'm going to have a giant image. So we'll say the magnification is negative di over do. And so that is negative of negative 33 divided by 100. The two negatives will cancel, and I get 1/3, so 0.33. Okay, so there's no negative here, so the image should be upright. M greater than 0, it's upright. It's upright. It's located at 33 centimeters, and this negative tells me that it's virtual. So rather than 33 centimeters being out here, it'll be over here. And it's going to be about 1/3 the height of my object. So I'm going to go ahead and draw a pretty big object so that when I get my image right around here that's 3 times shorter than this, it's not going to be too cramped. Okay, so let's start drawing this ray diagram with the easiest one first. So we'll draw the first one like this. So there's my first ray. It goes in through the center of the lens and it does not bend. My second ray, we'll do the in through F and out parallel, and then we'll do the in parallel and out through F. Okay, so if this was a converging lens, right, that bulged out, then our in through F would look like this. And let me actually draw what that looks like. Don't you draw what that looks like. But let's look at this and see why that doesn't work. So if I draw in through F and out parallel, then I'm actually going to get the location of an in focus image. And it's actually going to be right at 100 centimeters where I calculated it would be if I put in a positive F here. So that's what a converging lens would do. It would make an image at 100 centimeters. It would be upright, or it would be inverted and at 100 centimeters, and it would have a magnification of near 1, right? That height looks the same as that height. So that's the ray diagram that's in through F and out parallel that we would want if this was a lens that bulged out in the middle. But this is a concave lens that caves in the middle, and it will diverge our rays. So instead of coming in through F through this lens, we're going to go in through F on this side. So here's what that looks like. Is I'll take my ruler and I'm going here. Okay, so this ray is going to exit the top of the arrow and travel in a straight line until it hits the lens. And now, I can maybe draw some dashes here just to make it clear that it's on its way to this F. But it never makes it to that F because as it passes through the lens, it bends and goes out parallel. So it's going to bend and go out parallel. Okay, so behind the lens, I have these two diverging rays. They will never cross to form a real image, which is what I expected. And now I'm going to go ahead and take this line and trace it back behind the lens. And there we go. We see that these two lines are crossing. So we are probably expecting to see an image. This is 30, this is 40. So we're good on our location. It's right between 30 and 40. And it looks about a third the size. So this looks good. Let's get our last ray on there, which is we've done in through F and out parallel. So now we need to do in parallel and out through F. So we'll go in parallel. And now out through F. So we have to think about this again, right? Out through F, if I bend it and go this way, has that same problem that I had before. If I draw this ray looking like that, then these two rays are going to cross. They'll cross, one crosses here and one crosses here. Well, that's not good, right? We don't have any one spot where they all three cross at once. And we don't want any one of them to cross, right? We want these rays to all be spreading out as they pass through the lens. So I'm going to get rid of that one. And instead of going out through this F, it's going to go out, excuse me, out through this F back here. So it's going to bend and go out through that F. And now it bends and it goes out through that F. And now I'm going to trace back this ray in a straight line. So my actual ray goes that way. But if I trace it back, I have this spot here where all three of mine cross and they meet right around where 33 centimeters is, and they're inverted. Okay, so magnification, just to make sure we've written all the answers. Magnification was 0.33, and the image was 33 centimeters away from the lens, but it's a virtual image, so it's on the same side of the lens as the object. And just to make sure that I'm labeling all these things really clearly, this right here is the image distance, right? The distance from the center of the lens to the image, and this right here is the object distance. Okay, so I have a little cheat sheet that I have made that helps me know when I'm looking for either a lens or a mirror, what kind of an image to expect. Okay, so let's write that out. So let's look at, we've kind of already seen, right, that mirrors and lenses behave similarly. So if we have a convex mirror, that behaves like a diverging lens. So if I had incoming light coming in toward here, right, as the rays, don't want to write that on here. Maybe I'll write it here. Right, as the rays come in here, they're going to exit more spread out. So they're going to come in and they're going to spread out. That's what this convex mirror does. That behaves similar to how a diverging or a concave lens does. right? So if I have incoming rays of light through here, they will bend and spread out like that, okay? So it's kind of, it feels almost a little bit backwards because here's a convex mirror and a concave lens, but I'm telling you that their behavior is very analogous, okay? So for those lenses, mirror or a concave, which I like to call diverging lens, that has f less than 0, negative. And by analogy, a lens that is converging bulges out. So that's a convex lens, behaves similar to, so if I have incoming rays here, right, they will bend and come together behind this lens. Whereas here, if I have incoming parallel rays, this looks like our satellite dish. So the incoming parallel rays would all bend and come together like that, okay? So this shape of a mirror converges things, just like this shape of the lens converges things. So I'm going to treat them the same on my table as well. So this is going to be a concave mirror or a convex converging lens. Where you say that f is greater than 0, and that's positive. Okay, so just to draw this a little bit, so the convex mirror looks like that, and the concave lens looks like that, where the incoming light will be going this way. The concave mirror looks like that, with the light moving to the right, and the convex lens looks like that. Okay, so let's look at what image and object distances look like. DO is greater than twice the focal length. DO, the object is between the focal length and twice the focal length. And this last one, which I need to erase a few things to be able to write on my piece of paper, is for objects inside the focal length. So let's get that PhET simulation up, and we'll just sort of analyze what goes on for a lens. And that PhET simulation only works with this converging lens. So the PhET simulation will be for this setup right here, the converging lens. So we got our converging lens, and there we go. Okay, so we said that right here is a special spot. And the reason that this is a special spot is because the distance that the object is away from the mirror is 2 times the focal length. Do you see that? So the yellow X is the focal length. And so this distance from the focal length to here is equal to the distance from the focal length to the object. Okay? And right when this happens, this image is exactly the same size as this image. I get closer and the image starts to get bigger. I get farther away and the image starts to get smaller, okay? So we have this sort of, for every location, as long as we don't get, of course, inside the focal length, but as long as we stay to the left of the yellow X where our focal length is, we will have a real inverted image. But it's bigger if we're close to the focal point, and it gets smaller as we get far away from the focal point, okay? And then so let's write that down. So our webcam is, we just looked at these two, right? So if the object is greater than 2 focal lengths away, this will always be real. So that means that the image distance is greater than 0. And we always, as long as we are not inside the focal point, so as long as our object distance is not smaller than the focal point, we still have a real here. So when we use the thin lens equation, that formula will always plug in or we'll always get a positive number for the image distance. This is also a real image formed from any single mirror or lens will always be inverted. So, and the way that we know that the object is inverted is because we have the magnification is less than 0. So we have a negative magnification. And we said when we were far away from the lens, more than 2 focal lengths away, then we had a smaller image. So that would be to say that the absolute value of the magnification is less than 1. It's some decimal between 0 and 1. If we are inside between the focal point, the yellow F, and this two focal lengths away, then we have a larger image. And that is that the absolute value of this is bigger than 1. Okay, now let's look at what happens as the object gets inside the focal length. So if the object is inside the focal length, we have this. So let's start it really close to the lens. And there we go. I guess we need to be a little bit far enough away to be able to see it. Okay, so we have this upright image, and it is larger than this. This is a magnifying glass, right? A magnifying glass makes things look bigger. So it's no surprise that this is upright. And actually, it gets bigger and bigger and bigger and bigger and bigger as I get farther away, and it gets smaller and smaller and smaller and smaller as I get closer. But as I get close, I want you to convince yourself that the image never gets to be smaller than the object. It's still bigger, still bigger, still bigger, still bigger. And right here, they're like the exact same size. So they start at the exact same size, and now the image is getting bigger and bigger and bigger. So the image is always bigger than the object in this scenario. Okay, so we always have a larger image when we are inside the focal point. So this is m greater than 1. We always have a virtual image, and a virtual image from a single mirror or lens is always upright. So virtual and upright will always go together on this table. Real and inverted will always go together on this table. A virtual image goes in the lens equation as a negative number. And an upright image has the magnification is a positive number. So I'll write down that it's greater than 0. I don't have a PhET simulation for our for the other side of this table, but we'll have to just trust that this is this convex mirror. This is the security camera, right? Objects or your rear view mirror, right? Objects in mirror are always closer than they appear because this always makes a virtual, upright, and smaller image. So this will always be virtual, always be upright, and always be smaller. Right? So this is ditto, and this is ditto. It doesn't matter where the image is, it will always, or where the object is relative to the focal point, you will always form a virtual, upright, and smaller image from either a convex mirror or a diverging lens. So virtual, that is that the image is less than 0, so we have a negative image distance. Upright is that the magnification is a positive number, and smaller is that that magnification is a decimal between 0 and 1, like that. Okay. So in the PowerPoint, I have these sign conventions written out. So it's a good thing to just review or to have in front of you when you're working on the homework. Right, so the focal length is a positive number for a converging lens and negative for a diverging lens. And images and objects that are on the normal side are positive. Otherwise, they're negative. So the normal side, here's the normal side, right? The rays travel in the way that they would like to be, right? They travel through the lens and they converge here. That's a real image. If things are always forming on what you would expect to be the normal side, where you don't have to kind of trace back and see where it seems like those rays came from, then that will always be a positive image distance. If you have to trace back your lines, then you're working with a negative image distance and a virtual image. Okay, and the height of the image is positive if the image is upright and negative if it's upside down. And one last couple of things. What do you need to know for a test or for a homework assignment? For mirrors, I will only ask you to draw ray diagrams for concave mirrors that form real and inverted images. So that is that I will only ever ask you to draw. See if I can find it. Mirrors, all the way back here. Might not be in the cards for me to find it. There we go. I will only ever ask you to draw this ray diagram, okay, where we are forming a real inverted image. We'll never have sort of a virtual image from a mirror. So for mirrors, there's just one ray diagram. It's this one, okay? For lenses, I want you to know how to draw all of them, okay? So you should know how to draw diagrams for the converging convex and diverging concave lenses with the object either inside or outside the focal point. And so in this video, I did not do a diagram for a converging lens that looks like this, the normal one. That will be in the recitation videos. But we did do a converging lens inside the focal point and a diverging lens inside or outside the focal point. Okay, good luck, and I will see you with the next video.